Hey data files, welcome back to INST 314 Statistics for Information Science. We're continuing our journey on the chi-square, specifically the chi-square goodness of fit test. And in this video, topic 5.2, we're going to look at conducting the chi-square goodness of fit test and show you how to do it by hand. Now, in the previous videos, I set forth the foundations for the chi-square broadly and the goodness of fit test, and we introduced the concept for the degrees of freedom. I also mentioned the bonus video explaining how degrees of freedom work in concert with alphas and p-values, so take a look for those. In the next videos, we're actually going to be looking at how we can do this as well in Excel and in R. So let's get started on conducting the chi-square, the goodness of fit. Now, the math machine, the formula here for this is the chi-square, which kind of looks like an X, but it's the Greek letter chi, capitalized, then a large sigma value. And then we see a division point here. And in the numerator, in parentheses, we have f sub o, which is short for frequencies observed, minus f sub e, which is frequencies expected. Those are differenced and then squared, divided by f sub e. So what this really comes down to is we have the frequencies observed in a table distribution minus its expected value, square it, divide it by its expected, and then sum all of those differences, and that's the chi-square value. The degrees of freedom for it is equal to k minus 1, where k is the number of categories in your variable. Let's see a slight variation on this, though, is called the Yates continuity correction. This only kicks in when we have 1 degree of freedom. This is because that when we only have 1 degree of freedom, we have to adjust our calculations a little bit to compensate for the low value, so our probability tables end up working out properly. And there's 2 extra steps that go into the Yates continuity correction. The first one is that when we take the observed minus the expected frequencies, we take an absolute value of those. And then we minus 0.5 off of those. Then we go back into squaring it, dividing by the expected frequencies, and summing them up. So just keep in mind, Yates continuity corrections are for when we have 1 degree of freedom, and we also have 2 extra steps in that particular setup. Now, when we want to go ahead and report the chi-square in APA, which is the format we're using for class, we use the Greek letter chi squared, and then we set up, in parentheses, the degrees of freedom, comma, n, close your parentheses, x equals the chi-square value that you obtained through your test, comma, and then p as it relates to your alpha. Now, when we have that p as it relates to alpha, I only want you to use one of 3 potential outputs here. You could write p equals and then put in the exact p-value you have, regardless of your alpha. That allows your reader to be able to see the exact p-value of your chi-square and then choose for themselves at what level of significance they would accept it. Conversely, we could say p is less than alpha. Now, you don't write out alpha at this point. You put in the numerical value of what your alpha was. So if your alpha was 0.05 and your p-value was less than that, you would write p less than 0.05. Conversely, if your p-value was larger than your alpha, you would write p greater than 0.05, assuming your alpha is 0.05. If your alpha was 0.01, you would use that number, and so on. And I have an example up on the screen of how we might show it written out in APA format. These values here are just an example. They don't come from anything in particular. So let's go ahead and take a look then at how this might work with an example on answering students. We're going to pretend that we're in a classroom setup, and I start randomly calling on people to answer questions in class, kind of like how I already do. And I tell everybody that my choices to choose them are random. There's only 5 people in the class, and those students are called A, B, C, and D, and E. Now, that's short for their full names, but we're just going to call them A, B, C, D, and E. After 3 weeks, I've called on A and B 8 times each, C and D 4 times each, and E 1 time each. E was short for Ed, so if you see Ed on the slides, the E and Ed, same person. Now, the students are starting to think that something's weird because Ed hasn't been called on very often, where students A and B have been called on 8 times each. And they might start to think that my choice of calling on them is not random after all. So we can ask, is the distribution of the students I've called upon different from that which we'd expect to find? So let's go ahead and figure this out using a chi-square. If we were expecting them by chance, we could figure out that each student should have an equal chance of being called upon in this particular example, so that gives them a chance probability of 1 out of 5. In that case, how many times would each student have been expected to have been called upon? Well, I called on the students a total of 25 times. I figured that out because A and B were 8 times, and there's 2 of those students. C and D were 4 times, and there's 2 of those students. And then E I called upon once, and that comes out to 25 times. So if the chance of being called upon is 1 out of 5, and there's 25 times students were called, we would expect that each student should have been called 5 times, if everything is equal. So let's go ahead and take then and figure out how much this was and how much this is different from chance alone. The first step is to go ahead and subtract the values observed from those that we would expect and take the sum. Now, if I did this without the extra steps of the chi-square, and I just subtracted them and summed them up, I would get a 0. Now that doesn't work out very well, especially when it goes into a numerator. So we end up squaring our differences, very much like how we do with standard deviations, helping us avoid the 0 and giving us an absolute difference. So we go ahead and take the first student, A, was called 8 times minus our expected of 5, square it. Student B was called 8 times minus our expected of 5, square it. C, 4 times minus the expected 5, square it. Student D, 4 times minus the expected 5, square it. And student E was called 1 time minus the expected 5 squared. Now, that's not quite just going to be enough to do the chi-square. We want to be able to take and compare against the number expected and not let that so much depend on how many different times that we've been doing this. So then we'd complete with the rest of the chi-square that we're going to divide by the expected values and sum them up. So let's look at the rest of the math on this. Up at the top, I've already mentioned our differences squared. Each one of those is going to get divided by 5, the expected frequency. We go ahead and sum each of those up, and what the math ends up working out to is a chi-square total value of 7.2. Now, I want you to take a brief look here and see that our value is 7.2, but at that last step where we've summed them all up, one of those values was much larger than the rest, the 3.2. That one corresponded to student E, Ed, and student E was only called upon once out of everybody else, when he was expected to have been called upon at least 5 times. And so since E had the largest difference from what we'd expect to find, that student is going to be contributing the most weight into our chi-square value. This is going to be important later when we start talking about the weaknesses of a chi-square. So trying to figure out if we're going to be statistically significant or not, we turn to a chi-square critical value table. Now we're using alpha 0.05, and this is a screenshot of part of a chi-square critical value table. And if we go ahead and look up onto the first columns there, those are all your alpha levels. We'll isolate out alpha 0.05, and then we're going to look down its rows to where we said we had 4 degrees of freedom. 4 degrees of freedom because we had 5 students, 5 categories. Minus 1 is 4. So the chi-square critical value intersects where our level of alpha and our degrees of freedom meet, and in this case is 9.488. 9.488. Let's go back to the hypotheses and work our way through it. Now, the null said that there's not going to be any differences between them. So we would assume that students A, B, C, and D have the equal chance of being called upon, and that is about 20% each, or 1 out of 5. The alternative says that at least one of these proportions is wrong. One of these is false, and therefore the distribution is not what we would expect to find of them all being equal. Note when we're talking about these in the chi-squares, we never say that which proportion is false of all the students A through E. We just know that at least one of them is not 1 out of 5 or 20%. Now we went ahead and calculated the chance of getting a sample extremely large as ours, and so we looked at the chi-square we obtained was 7.2, our degrees of freedom were 4, and the chi-square critical value was 9.488. So do we reject or fail to reject our null hypothesis? Well, let's go ahead and look at these values again, 7.2 against that 9.488. If we were to plot this out on a curve, we can see that there's this chi-square distribution, and our chi-square critical value of 9.488, I've rounded to on this graph is to 9.5, and from that point towards the right is our shaded red critical region. Then I've also mapped onto this distribution the chi-square value we've obtained, 7.2, denoted by the blue dotted line going down into the distribution. If our chi-square critical value gets into the red, meaning it is at or larger than our chi-square critical value, we are statistically significant. However, in the graph on the screen, we see that 7.2 is not as large. It is smaller than our critical value of 9.88. It is not in the shaded region, and therefore it is not statistically significant. So in this case then, we can say that we failed to reject the null hypothesis, and that I was indeed calling on the students A through E randomly enough that the distribution that we've observed is not actually different than that we would expect to find. Lastly, I want to leave you with just a few different functions and options that we use in R when we're doing our chi-squares. You're going to see some of these come back up into effect when we do the R walkthrough video, but I just wanted to at least give you a shot of them here and kind of mention a little bit of how we might be using some of these. And with that, I'll see you all in the next videos when we do our walkthroughs of the chi-square in Excel and R.